What's up? This is Statics of Rigid Bodies and my name's Kyla Marie M. Kaheme, and right now we will be tackling about trusses, analyzing trusses to be exact. However, this video will only be focusing about the method of joints. Because if I try to fit the two methods in one video, it will be long and that would be hard to manage. And so I decided to do on only one. You could try to search up the other method of sections in the internet if you want. And you could consider these as an introduction. So before we begin, let us first define a truss. A truss is a structure composed of slender members joined together at their end points. These members are organized into a connected triangle so that the overall assembly will behave as a single object. A truss is made up of a web of triangles joined together to enable the even distribution of weight and the handling of changing tension and compression without bending or shearing. The triangle is geometrically stable when compared to a four or more sided shape, which requires that the corner joints are fixed to prevent shearing. So as said, trusses consist of triangular units constructed with straight members. The ends of these members are connected at joints known as nodes. They are able to carry significant loads, transferring them to supporting structures such as load-bearing beams, walls, or the ground. In general, trusses are used to achieve long spans, minimize the weight of a structure, reduce deflection, and support heavy loads. Now we have here some structures where trusses are applied. We have roof of factory shade, warehouses, railway platform, garage shed, transmission towers, crane trusses, bridge truss, and sports stadiums truss. So much for that, let's proceed to analyzing trusses. When it comes to analyzing trusses, we use two effective methods, the method of joints and the method of sections. But just like what I've said earlier, we will be only tackling about the method of joints. What do these methods analyze, you ask? Well, using basic equilibrium equations, it analyzes if the trusses are statically determinate or not. To put it in simple words, it tests how stable the structure is. Let me enlighten you. Method of joints. From the word itself, joints. In this one, you could say that if a truss is in equilibrium, then each of its joints must also be in equilibrium. Let's try solving this sample problem. We have here a truss bridge, and we are asked to find the forces acting on each member, and to specify whether the forces in each member is a tension or a compression. So we got a total of 9 members. 1, 2, 3, 4, 5, 6, 7, 8, 9. The forces in these members are what we are going to find. So the first step is to draw the free body diagram and find the reaction forces, while treating the whole truss as a rigid body. Now there are forces supporting the bridge. In this point, we got a force going up and a force going to the side. It's a pin joint that prevents the motion in both the X and Y direction, while in point F, we'll only have a force in the Y direction because a roller joint only allows to slide back and forth. Hence, there is only an upward force that prevents it from falling down. So, we can now take the sum of the forces in the X direction, which is 0. While the sum of the forces in the Y direction is equal to R1Y plus R2Y minus 60 kN minus 80 kN equals to 0. So we got two unknowns here, R1Y and R2Y. Let's have this as equation 1. Now let's proceed to the moment equation. First, the moment about point A. So the sum of the moment about point A is equal to negative 60 kN because it is a downward force times 10 meters minus 80 kilonewtons times 20 meters plus R2y. This one is this one is one of the reaction forces, times 30 meters, which equates to 0. Let's say this will be equation 2. So if we use this equation, we can solve for the R2y, which is equal to 73.33 kilonewton. Substituting the value of R2y in the first equation, we will have R1y is equals to 66.67 kilonewtons. Now that we have our reaction forces, we can start to solve for the forces in individual joints. So we will be starting with point A because it has two reaction forces. We have here R1y, which is 66.67, and R1x, which is 0, right? We also have the first two unknowns, force AB and force AC. And of course, this member is in 20-degree angle. Assuming first that all forces were in tension, we have the sum of the forces in X, which is FAB plus cosine 20 of FAC equals to 0. Now for the sum of forces in the Y direction, we have 66.67 kilonewton minus sine 20 times FAC equals to 0. Using this equation, we can solve for the force AC. So 66.67 kilonewton over sine 20 is equal to 194.93 kilonewton. This one is a tension force because it is positive. Now, substituting the value of FAC to equation 1, we can solve for the value of FAB. Negative cosine 20 times 194.93 kilonewton, which is equal to negative 183.17 kilonewton. So the negative here indicates compression. So we have solved the first two forces that are acting on our truss. Now we just have to repeat the procedure until we find all unknown forces. Going back, we can't proceed to point B yet because there are 3 unknown forces. So just like what we did earlier, it is better to find a point with only 2 or less unknown forces because we can only make at least 2 equations. So let's first go to point C. Now, we know that FAC is in tension, so we are certain that the force is pulling from the point. We also have a known force, BC and CE, and again, this one is in 20-degree angle. So the sum of forces in the X is equal to negative cosine 20 multiplied by FAC, which is 194.93 kilonewton, plus FCE equals to 0. Now, for the sum of forces in the Y direction, we have sine 20 multiplied by FAC, which is 194.93 kilonewton, plus FBC equals to 0. Let's first solve for force CE. So cosine 20 times 194.93 kilonewton is equal to 183.17 kilonewton. And because it is positive, it will be tension. Next, for Y direction, we have FBC equals to negative sine 20 times 194.93 kilonewton, which equates to negative 66.67 kilonewton. This one is in compression. Now, we only need 5 more unknown forces to solve. And since there are only 2 unknown forces in point B, we can move on to that joint. Here's the free body diagram. So we now know that force AB, which is 183.17 kilonewton, is in compression. So it is now pushing rather than pulling. And in FBC, we have also a compression force which is 66.67 kilonewton. And we have a load pushing downward with 60 kilonewton force. So now, we will be drawing the unknown forces FBD and FBE. Again, this angle is 20 degrees. For equation 1, we have summation of Fx is equal to 183.17 kilonewton plus FBD plus cosine 20 multiplied by FBE equals to 0. For equation 2, we have summation of Fy equals to 66.67 kilonewton minus 60 kilonewton minus sine 20 multiplied by FBE, which is also equal to 0. So, jumbling up the equation, we can first solve for FBE. So, FBE is equal to 66.67 kilonewton minus 60 kilonewton over sine 20, which equates to 19.50 kilonewton. Next is solving for unknown FBD. Substituting the value of FBE, we have negative 183.17 kilonewton minus cosine 20 multiplied by 19.5 kilonewton, which equates to negative 201.49 kilonewton. So we have here FBE, which is equal to 19.5 kilonewton. This one is in tension force. And also we have FBD equals to 201.49, which is in compression. Moving on to point D, we have a compression force of 201.49 and a load of 80 kilonewton. We also have to solve for two unknown forces, FDF and FDE. So the first equation, summation of Fx is equal to 201.49 kilonewton plus FDF equals to 0. If we solve for that, we'll have force DF equals to negative 201.49 kilonewton, which is in compression. And for summation of Fy, we have negative 80 kilonewton minus FDE equals to 0. And again, solving for this, we'll have negative 80 kilonewton, also in compression. Now we only need one unknown force to solve. Lastly, we have point F. So this upward force is the reaction force, R2Y. And we also have FDF, which is 201.49, which is in compression. And of course, the unknown force, EF, in 20-degree angle. So summation of Fx is equal to 73.33 kilonewton minus 20 multiplied by FEF. Solving for the last unknown force, we have FEF is equal to 73.33 kilonewton over sine 20, which equates to 214.40 kilonewton in tension. Finally, we have completed the diagram and solved for all external forces, reaction forces, and all internal forces acting on each member. Just a tip for you guys, in solving simple trusses, we often have the symmetric system and zero force members. You should pay attention to that, because identifying these special cases sometimes will make the whole analysis way easier. You could just solve for the other half and copy the results to another half. Easy, right? So that's it. This ends my report. I hope you enjoyed the discussion, and thank you for listening.